Okay, thank you very much, everybody, for coming. Thank you very much to the organizers for giving me the opportunity to talk, for organizing the conference, and for giving the impression that everything is under control and working well. I think that's the impression that I'm getting, so it's going okay. My name is Bradley Kavanagh. Yes, this pointer really doesn't work very well, so I might have to jump up at certain points. Bradley Kavanagh, I'm a postdoc at IFCO, which is in Santander in northern Spain. And it's a great honor to give the first talk of the conference. I think this is the first talk, also the first talk about dark matter, of course. So I think I'm contractually obliged to say something kind of general about dark matter. And we know dark matter exists on all scales, it's present in the universe on all scales. Okay, we know from cosmological observations of the CMB, large-scale structure, that we need dark matter to form the structures that we see. You could kind of take a patch of the universe and zoom in to the largest gravitationally bound structures in the universe, galaxy clusters. You can weigh galaxy clusters with X-ray observations and gravitational lensing, and we know that these have huge mass-to-light ratios. So there's lots of stuff in galaxy clusters that we don't see. And of course, you can keep zooming in. You can look at individual galaxies and galaxy rotation curves, and we know in our own galaxy, there is missing matter, which is helping to keep the galaxy rotationally supported. And so you kind of keep zooming in and you think about the landscape of dark matter searches that we're trying to do on Earth or near Earth. And these usually have fallen into kind of three broad categories, at least for the classical WIMP scenario. So one of them is indirect detection. You try and look for dark matter particles producing standard model particles in the galactic halo, or other dense environments, and you look for those standard model particles. You can try and produce your dark matter in a collider, collide two particles together and produce dark matter, or you can build a kind of low threshold, very large underground detector, which tries to look for dark matter in the galactic halo interacting with nuclei or electrons or whatever in your detector. And we're going to hear, well, so the kind of, to me at least, the way that you move forward with these experiments is to build better experiments. Okay, it's you want to go to different ranges of photon energies, for example, or you want to build a telescope which can collect a very small number of photons and be sensitive to a very small flux. Or you want to build a direct detection experiment which can access very low amounts of energy which are deposited in your detector. And we're going to hear quite a bit about these different approaches. I've kind of pinned a few different parallel sessions that mention these things. But I'm going to talk today about a kind of completely orthogonal direction, where the goal is perhaps not to build a better detector or explore the parameter space in that way, but instead to look at dark matter in very different environments to the ones that we're used to. Okay, and that's why the talk is called Dark Matter in Extreme Environments, because I'm going to talk about dark matter around black holes and also dark matter around neutron stars. And what this gives us is it gives us higher densities of dark matter, potentially. It gives us higher densities of ordinary matter, especially in the case of neutron stars, large magnetic fields, long time scales to work with. And hopefully over the rest of the talk, I'll explain exactly why this could be a very promising way to go with dark matter searches in general. Okay, so let's start with black holes. So we kind of know that black holes like to gather things around them. This is, a stupid thing to say, really. But if you throw a bunch of gas at a black hole, you form a dense accretion disk. If you have heard of superradiance, what you can do is, if you have scalar fields in the universe, then you can build a very dense cloud of light, ultralight bosons around black holes. What I'm going to talk about is a slightly different thing, which is the formation of what I'm calling spikes, dark matter spikes, or dark matter dresses. Okay, and there are kind of two scenarios where you could do this. You could build a dense spike of particle dark matter around a black hole. And one of them is when you have a black hole which is growing slowly at the center of a dark matter halo. And when it does that, it sort of contracts the dark matter halo and gives you a very large density of dark matter. Or if the black hole that you're thinking of is primordial, so if it's formed in the very early universe, then as the universe becomes more dilute, the sphere of influence of that primordial black hole grows, and you collect a spike of dark matter around the black hole. Okay. And so sometimes we parameterize this spike as having a density profile that just goes like a power law, so it rises very rapidly towards the center. But in fact, not all dark matter particles can form these spikes. Okay, I mean, the kind of canonical WIMP doesn't form such dense spikes, partly because it can self-annihilate. And so if you have this huge density of dark matter, then you'll start to suppress the density in the spike. Okay, and so these colored lines correspond to different slopes of your spike, so how rapidly the spike rises towards the central black hole. But if you have self-annihilation, then you start to get a core. Okay, you suppress the density because all those particles very close to the center, which are densely packed, will annihilate away. Okay, but if you have some kind of non-annihilating dark matter candidate, like an axion or asymmetric dark matter or something like that, then you can certainly produce a spike which is huge in terms of density. Okay, so locally to us around the solar system, we have a dark matter density of about 10 to the minus 2 solar mass per cubic parsec. But in these spikes close to the center close to the black hole, you can reach densities that are 20, 25 orders of magnitude larger than that. Okay. So we have this system of dense dark matter, and the question now is, how do you want to try and detect it? And the way that I'm interested, or the systems that I'm interested in looking at, are called intermediate mass ratio in spirals. Okay, so you have a central black hole, and then orbiting around is a smaller black hole, a lighter black hole, which is 100 or 1,000 or 10,000 times lighter. So actually, this small black hole could be a black hole or a neutron star. It just has to be much lighter than the central object. Depending on the masses of these things, you would be able to detect these systems in gravitational waves using different observatories, using different gravitational wave detectors. So if you're thinking of something very light, like a one solar mass object at the center, then you'd be able to see this with LIGO or Einstein telescope. If instead you're thinking of something heavier, like an intermediate mass black hole at the center, then we're thinking of LISA, which is a future space-based gravitational wave detector. The signal that you would see from these systems is the gravitational wave strain, so the size, the amplitude of the gravitational waves that you would see, just looks like a kind of sine wave as this system orbits. But as it emits gravitational waves and starts to shrink, the amplitude of the gravitational waves increases, but also so does the frequency. Okay. And what happens if you have a dark matter spike here is that you change the rate at which this system inspirals, because you're not losing energy just due to gravitational waves, you're also losing energy due to dynamical friction with the dark matter particles in this spike. Okay, so this is a purely gravitational effect. Essentially, the small compact object is scattering gravitationally with dark matter particles in the spike, and it causes this system to inspiral more rapidly. So you could imagine starting at the merger and tracing this thing backwards, looking at how the orbit evolves. And initially, these two things are in phase, but then because they're inspiraling at a different rate, you see that you get this phase difference between the two, okay, just because they're inspiraling at different rates. Okay, and so this process is sometimes called dephasing. This is the thing that I'm looking for, that we're interested in looking for, in order to try and detect dark matter around these black holes. So it turns out that you have to do some reasonably complicated modeling, and in fact, we've only done the first steps of this modeling. So what you have to do is you have to evolve this system, taking into account the emission of gravitational waves, which shrinks the orbit, and dynamical friction, which shrinks the orbit. But you also have to evolve the distribution of dark matter particles in your spike, because this gravitational scattering also injects energy into the dark matter spike. And so you can, here we use a semi-analytic prescription to follow the distribution function of dark matter particles as you inject energy. And so what you find is you sort of initialize this system at some separation, and then you start running your simulation forward, and what you find is that you very quickly deplete this spike. Okay, you're scattering dark matter particles, and so they start to get ejected or pushed away. And then your system inspirals, if you sort of evolve this a bit further forward, And the dark matter particles kind of get pushed further and further out, okay? And always at the point where your small compact object is, you have this kind of depleted spike. And so it was previously believed that this effect of dephasing could be huge, like you could take, I don't know, a 5-year in spiral and in spiral in less than a year. But in fact, because of this effect, this kind of feedback effect on the dark matter halo, it's actually a much smaller effect. It's maybe a 5-year in spiral, actually including dark matter, is just shortened by a few days or so. Okay, but you can keep going, you can evolve this forward, and you can work out exactly what this trajectory of the binary is, what the separation of the binary is as a function of time. And from that, you can work out the gravitational wave frequency as a function of time, and the gravitational wave strain as a function of time. And we now kind of have some machinery to be able to build this gravitational wave strain using these calculations. We haven't been able to perform these searches yet. One of the reasons is that we've been focusing on systems which are heavier than can be detected with LIGO, for example, and so we would be looking at future detectors to do this. But we can ask questions like, can we distinguish this kind of gravitational waveform from a system in vacuum, okay, where we have no dark matter, no nothing else? Would you be able to look at one of these waveforms and be convinced that it actually has, convinced by the presence of dark matter? Okay, and so again, this is a system, a kind of intermediate mass black hole being orbited by a 1 solar mass object that you would be able to see with LISA, for example. And so what we went away and did in this work that was led by Adam Coogan, we calculated the Bayes factor, so the Bayesian evidence in favor of this pure vacuum system versus the system with dark matter, and tried to work out, can you see evidence in favor of the dark matter spike? And so these black contours show you different values of this Bayes factor. And if you're not familiar with this, anything above, say, 100 or so, you would certainly say is convincing evidence that there was a spike there. And I've put some dots here which kind of point to the typical properties, the density and the slope of this spike in the benchmark scenarios that I talked about for the formation of these spikes at the beginning. This whole white region in here is white because it turns out it's very hard to even find a waveform, a vacuum waveform, which looks like your dephased dark matter waveform. Okay, and so what we showed with this is you should be able to tell if you can pick up one of these dephased waveforms, you should be able to tell that it's actually that it actually has some dark matter in there. Okay, it's not just a vacuum. Another question that we get a lot is, can you distinguish this from other environmental effects? Okay, like I said, black holes like to gather stuff around them. In some cases, they have pretty dense accretion disks. And so what we did was we generated some waveforms, assuming that you have this dense accretion disk, which also produces some kind of dephasing. You try and fit that data, fit the waveform using a dark matter spike. I think the thing that I'd like to point out is that when you do that, you try and reconstruct your posteriors for the properties of this spike, even though it's not really a spike. You find that the reconstructed dark matter density is peaked at 0. Okay, so it's very hard to confuse an accretion disk with a dark matter spike. If you try and fit with a dark matter spike, your data tells you that actually there is no dark matter spike there. You're seeing something, but it's not a dark matter spike. And so we're reasonably convinced now, and this is work in progress led by Pippa Cole in Amsterdam, reasonably convinced now that we should be able to distinguish this from other environmental effects. And then you can go away and do the other exercise, which is if I actually do have, if I generate my data using this dark matter spike system and then try and reconstruct the properties of that system, it turns out that you can do that very well. So on the left here is one of these benchmark scenarios where we're looking at detection with LISA. On the right, the primordial black hole scenario, where you can in principle have black holes which are much lighter, which still have dark matter spikes around them, and which therefore could be accessible with maybe not LIGO because the sensitivity isn't there, but with Einstein telescope, which is a future ground-based gravitational wave detector. And the point here is that you can actually pick up the value of the density. Okay, you can tell that there's a spike there, and you can actually tell something about the shape of the spike. Okay, so you can tell like the normalization of the spike. I think that the interesting thing about this, the thing to take away perhaps, is that first of all, if you could do this, if we were successful in doing this, you would immediately have a detection of dark matter or of some unusual environmental effect which doesn't look like an accretion disk. And if you do that, you also can immediately tell something about the nature of dark matter. Okay, because like I said earlier, not all dark matter particles produce these spikes. Okay, so self-annihilating dark matter doesn't produce these spikes just because it starts to annihilate away. Fermionic dark matter can't compress the phase space enough to produce such dense spikes. Ultralight bosonic dark matter just behaves in a very different way and starts to exhibit wave-like behavior on the kinds of scales that we're trying to compress the dark matter down into. And so you would immediately start to be able to say things about the particle properties of dark matter, even though the signal itself doesn't depend on any kind of particle physics interaction. It's purely a gravitational interaction. Okay, and so you can, in principle, probe dark matter over a huge range of masses, but you would still be able to hopefully get some information about the particle physics properties out of this. So, like I said, we're not quite at the stage where we can do these searches, but we're getting there, partly because we have to wait for the right detectors to be built, partly because there's lots of modeling still to do. I won't go through all of this, but what I will say is I'm very interested in particular, trying to model these systems more carefully to see how they behave. And so we're in the middle of writing some n-body code so that we can actually fully simulate this without having to resort to kind of semi-analytic models to see exactly how this system behaves and extract waveforms and eventually get to the point where we can do some kind of template fitting and search for these systems. Okay, so that was one kind of extreme environment. Now we're going to change tack and talk about a different kind of extreme environment, which is neutron stars. Okay, so this horrible mishmash of images that I put together demonstrating what a neutron star doesn't really look like. So the reason that neutron stars are so great when it comes to dark matter searches, well, there are a few reasons. One of them is that they have a strong gravitational field, so as dark matter falls in towards them, you basically compress the phase space density, you compress the physical density of dark matter. And so essentially you can capture more dark matter than you would otherwise with something which is less heavy, less dense. They act like giant direct detection experiments. Okay, they have huge target densities. This is like one giant nucleus. And so it actually gets to the point where with a neutron star, a dark matter particle passing through it will almost certainly scatter and almost certainly be captured, as long as it has the kind of cross-section that we're searching for in current direct detection experiments. Okay, so there's quite a lot of complementarity there. And then what will be most important in a second is that neutron stars, especially young neutron stars, can have very strong magnetic fields. Okay, so I'll briefly say something about this dark matter capture question. And one of the reasons that neutron stars are so interesting is that there are lots of things in the universe which can capture dark matter. Okay, so you can capture dark matter in planets and in main sequence stars. The problem is that once that dark matter scatters and is captured, it tends to thermalize, and then the high energy tail of that thermal distribution tends to evaporate away from the star if the dark matter is too light. Okay, and so what I'm showing here from this paper is at what mass this evaporation becomes a problem. So if you're below, say, 1 GeV, it's very hard with ordinary celestial objects to stay captured and to have any kind of effect on them. Neutron stars, on the other hand, because they're so dense, can keep things captured down to keV masses. And so I think there are a few talks on Thursday afternoon talking about this kind of capture process and related things. So I'll move on from that. So as I said, the other extreme thing that we get with neutron stars is that you can, in principle, have very strong magnetic fields around neutron stars. And why is this interesting? Well, one particularly well-motivated dark matter candidate, okay, it's maybe the kind of second contender after the WIMP, is the axion. Okay? And axions interact with the electromagnetic field, and they can convert into ordinary photons in the presence of a strong magnetic field. And so what has been done now for however many decades, last 10, 20 years, is that people have been building Earth-based detectors, lab experiments, trying to look for this conversion of axions into photons by building basically a radio cavity, a resonant cavity, surrounding it with a strong magnetic field, and then you look for radio photons coming out. The reason that it's radio photons you're interested in is just because of the typical mass range of what's called the QCD axion. Okay. And so people have been doing this for however long, kind of trying to slice through this parameter space, looking for this coupling between the axion and the photon. And it's kind of hard to do because you need to tune your resonant cavity to match the mass of the axion you're looking for. And so it's really painstaking it's really painful to kind of do all these little slices down into the parameter space. And what's cool about neutron stars is that you can do something very similar, except this resonance happens not when you've tuned the size of your cavity, but when the mass of your axion matches the plasma mass in the plasma around the neutron star. And it turns out that plasma mass varies as a function of radius away from the neutron star. And so with one neutron star or with a bunch of neutron star observations, you can kind of scan a large number of masses. And so this field is, in some sense, still finding its feet, but you can see this green region is one particular radio survey looking for neutron stars emitting these radio waves in the center of the Milky Way. And you can start to span a reasonably wide range just with one set of observations. Okay. Let's see. So an alternative thing is that, what I was saying there was basically that you could have axions just in the Milky Way halo or in galactic halos, which are converted into photons. In some axion models, you actually don't have a kind of diffuse, or it's not completely a diffuse dark matter axion field. In fact, you have clumps or mini clusters of axions. Just from the time and the way that these things form, you can have clumps of axions. And so what we did in a couple of papers a couple of years ago now was think about what happens when one of these clumps of axions passes through a neutron star, or rather the other way around, because the neutron stars are very compact compared to the axion mini clusters. Okay. And what you get in that case is also a radio signal, but it's a radio transient. Okay. And so these things can last a few hours or a few days, depending on exactly the size of these mini clusters. But what you could then go away and do is look for these radio transients in the Milky Way or in other galaxies. Okay. One of the cool things is that because you've taken a lot of your axions and bound them together in a clump, the density in that clump is quite large, and so the flux of radio that you get can be very large. And so you don't necessarily need a lot of observation time to find a very low flux. You can just kind of look for a little while. This is an example from a proposal we wrote where you're just looking for a couple of 2-hour windows and seeing what you can see. So I think it's a very similar situation to the case of black holes and dark matter, in the sense that there's still plenty that needs to be done. Modeling these neutron star magnetospheres and understanding exactly how many neutron stars have the magnetic field properties that we would need is kind of an ongoing challenge. But I'm particularly excited about the fact that we're actually doing these observations right now for looking for these radio transients. And so with some colleagues in the University of Virginia, we're actually using the Green Bank telescope to look at Andromeda. And if you look at Andromeda, you can almost image the whole galaxy in one go and look for these radio transients. So hopefully in the next few months, the next 6 months or so, we should have some results on that search. So as you can tell, there's lots still to do. in both of these directions. Luckily, I'm not doing it on my own. These people have to suffer through me. So I've listed a bunch of collaborators, probably not an exhaustive list. I've also tried to highlight some of the younger PhD students and postdocs who are probably doing the lion's share of the work on these projects. But there's plenty still to do, and we're really working on it to try and do that. So I think the thing that I wanted to leave you with is just the idea that there's this orthogonal direction that we can do we can do dark matter searches in. Okay, we can access higher densities, higher magnetic fields, just in general more extreme situations that you wouldn't have access to in the lab. But there's also plenty to do. Okay, so hopefully I've convinced you that it's worth doing those things. We have less control in some sense over these environments, but we still have the possibility to gain a lot of information about dark matter if we can actually do these searches. Thank you very much. So the question, just in case people can't hear on the live stream, is how does this situation change if I have dark matter around both of these black holes? So my feeling, so we haven't strictly looked at that, but my feeling is just that tidal forces from the larger black hole would quite quickly strip away the smaller dark matter halo. What typically happens is that the size and mass of the dark matter spike is correlated with the mass of the black hole. And so the smaller object is probably going to have a much smaller spike. And so it's either going to be stripped away or just going to be less relevant in the calculations. Yep. So yeah, so the problem that I didn't really, in fact, maybe I can use this. So so the question was, what happens instead of using intermediate mass ratio in spirals if you have something which is close to a 1-to-1 merger? The reason that we're interested in a large mass ratio is that the smaller object just acts like a perturbation of whatever environmental effect is there, like whether it's an accretion disk or a dark matter spike or whatever. And so you deplete this dark matter spike kind of temporarily almost. But if you have an equal mass ratio, the amount of energy that gets injected means that you basically destroy the spike very, very quickly. Yeah. What are the things that affect the rates? So this is something that the actual rate calculation seems to be time dependent in the sense that every time we redo the calculation and try and account for something else, we find that something else is important. So at the minute, we're thinking that throughout a whole galaxy like Milky Way or Andromeda, we're probably talking 10, on the order of 10 encounters between a mini cluster and a neutron star per day. Okay, but so that's summed over all possible. That's not looking at one specific neutron star. It's looking at the whole population. And one of the important things that comes up, if I can find the slide somewhere, is that close to the center of galaxies, these mini clusters get disrupted by encounters with stars. So encountered stars inject energy and basically strip away the mini clusters. And so there's kind of an interplay between where the neutron stars are and where the young neutron stars are, which have a strong magnetic field, and where the surviving mini clusters are. And so we're kind of still trying to pin down exactly how this dynamic works. Yeah. No, it's there we go. So this is a small effect, and something which I didn't emphasize is that it is a very small effect, but it accumulates over potentially many cycles. So the kinds of systems, if you're thinking of looking at one of these intermediate mass black holes with LISA, you would be looking at many millions of cycles, and then what you actually need is only a few cycles. So actually here, this coloring here is the difference in the number of gravitational wave cycles during the in-spiral between your dephased system and the best fit vacuum system, where you've tweaked the masses as much as you can, and it turns out that you just need a few cycles of dephasing over millions, and you can still detect this effect. Yeah. It's or essentially you have the long time scale kind of lever arm to be able to see the difference in the phase over many cycles, many years. Thanks. Yeah. Yeah. So this. So I think it's this paper here, 1912, that tries to deal with this issue. There's like a Doppler shift that you get in the frequency during the rotation of the neutron star, and so in principle you could pick that up. The problem is that you kind of the axions don't convert in a kind of spherical way, so that the signal that you get is not perfectly isotropic, and so it comes with some complicated anisotropy, and that makes it quite hard to pick up, for example, the relative orientation of like the magnetic field and the rotation, or the magnetic field and our line of sight. So it's complicated, I would say.